Hey guys, welcome back to another RASK Maths video, and in this video I'm going to be talking about the Newton-Raphson approximation method, which can let you solve basically any equation in maths. So you might be thinking, why don't we always use this? Well, the reason is this is an approximation method, so although you can solve any equation, you're never going to get an exact solution. But if this is for practical purposes, such as, working out, something to do in applied maths or a physics problem, then you can figure out the answer to any equation you want and then just use that answer to as many decimal places as you need. So for all practical purposes, this is basically one of the best methods ever created. And yeah, I'm going to be showing you guys how it works and then using it to solve this curve, which this is the equation we have here, y equals sine x plus e to the x, and you cannot actually solve this normally because sine x and e to the x are both transcendental functions, so you can't solve any of that. And yeah, the only way to find a solution or the root when this is equal to 0, which is somewhere around there, would be to use an approximation method. So yeah, let's just first derive it and then show you guys how it works. So let's just say I had a random function f of x, and I'm just going to draw it like this. No, it needs to have a root. Okay, let's do something like this. Alright, here we go. So what I'm going to do is, the way this method works is, here's a high-level overview. So we pick an initial starting point, let's call this x0, and we go to the point on that curve, and we basically create a tangency line. So for this point here, tangency line would be something like this. Then we see where this tangency line intersects, and we make this x1, and then we do it again. We go to the point where this point of x coordinate is, and we just do it again. So we'll create another tangency line, and then you can see here, this second tangency line has taken us much closer to this root, and we can call this x2 and just keep repeating that until we get as close as we want to the root, which is somewhere over here. Now the reason this works is because at any point on a curve, a straight tangent is the best approximation of that curve at that point. So using a straight approximation, using a straight tangent, we can easily work out the x-coordinate where that will intersect the x-axis, or essentially we're working out the root of this tangent. And then we use this new root, which is probably going to be a better approximation to the original function's root, pass that back in and create a new tangent. This new tangent's root is going to be closer to the original function's root, and we just keep doing that. So each time the tangents get closer and closer, the tangent's point of intersection with the x-axis, or their root, gets closer and closer to the original function's root. And that's how we're able to find what that original function's root was to an arbitrary number of decimal places. Now, let's actually make some equations. So let me draw out another sort of graph. Let's do something like this. And yeah, so let's say we started over here. x0 is over here. And I'm going to call this function y equals f of x. So if we go up to the point of this x0, this is the point x0 and f of x of 0, right? That's pretty self-explanatory because this is y equals f of x. Now, we know the gradient at this point. Let's see if I can draw a better tangent. So we know the gradient of this tangent is going to be equal to, well, f dash of x0, because the gradient is defined as the derivative at that point. So that's what we have to do. So the gradient of this is f dash x of 0. So now using this, we have the gradient and we also have the point. And using just those two bits of information, we can work out the equation of that tangent. So let's just write this. This tangent has equation, well, I'm going to use the expression y minus y0 equals x minus x0. So that gives us y minus y0, or the point, which is f of x of 0, is equal to the gradient, which is f dash of 0, f dash x of 0, multiplied by, just going to go on the next line, x minus x of 0. So let me bring this over here. In other words, what it's saying is the tangent has equation f dash x of 0, x minus x0 plus f of x of 0. Now, if we want to work out the root of this tangent, we just have to set y equals 0. And setting this left side equals to 0, doing some rearranging, you end up with x minus x0 is equal to minus f of x0 over f dash of x0, like so. And then this is just going to tell you that the new root, or I'm going to call this x1, is equal to x of 0 plus, sorry, not plus, minus f of x of 0 over f dash of x of 0. Now remember what this actually is. This is the root of the tangent, so this point here. And this is our new approximation for the root. And we can just keep on doing this until eventually we get to the desired root. So this formula here is not actually just, it doesn't just work once, but it's actually an iterative formula. X of n plus 1 is equal to x of n minus f of x of n over f dash x of n. And yeah, this is the iterative formula which the Newton-Raphson method is essentially using to just work out what the root is. Now, one thing you'll notice is it's only going to identify one root, because once it gets close to a specific root, it's just going to narrow in on that root and it's not going to go any further. So if we were to start here, we would end up just honing in on this root. So using the Newton-Raphson method, we're not able to identify every root of a polynomial. You have to start close to the root you want. So if we wanted this root over here, we might start somewhere over here. And then that would just create these sort of things like that. So that's one drawback, is that first of all, you don't get an exact answer, and second of all, you don't get all the roots. So you need to have some sort of idea of where the roots are initially, but that can easily be done using graphing software or just interval testing. So yeah, here's our formula. Now I'm going to go back to the top and I'm just going to write it out and work out the solution to this this unsolvable equation using regular methods. So iterative formula is x of n minus f of x of n over f dash of x of n. Now, we're solving for when f of x equals 0. So what I'm going to do is define f of x to be sine x plus e to the minus x. Now, if we're solving for f of x equals 0, that's going to give us this point here. Let's work out the derivative, which is going to be cos x minus e to the minus x using the chain rule. And then let's make my iterative formula. So x of n plus 1 is equal to x of n minus sine of x of n plus e to the minus x of n all over cos of x of n minus e to the minus x of n. And now all we have to do to use this iterative formula is pick a value. So I'm going to pick an initial starting point of, let's say, we can do 2, 3, or 4. I think I'll do 3, just because it's close and, you know, it's a good starting point. So let's use x0 equals 3. I'm just going to type this into my calculator and use the answer function to give me that iterative power. Alright, so I've typed it into my calculator. Now we get x1. Oh, sorry. I'm not in degrees. I'm not in radians. Okay, so let me do this again. Okay, so first answer we get is going to be 3.1836. Just rounding it to a random number of decimal places. You'll see it should converge as we add more and more, as we do more and more iterations. So the number of specific decimal places doesn't really matter. But next answer we get is 3.183063. Another one. Oh, so basically already converged. The next one is going to be 3.18306312. So you can see it's already starting to converge. And yeah. So what this tells us is we can just say the root x is approximately equal to 3.183063. I'm just going to say that. Cutting off after that doing decimal places. So tying this back, we can say that x is approximately equal to, because remember this isn't exact, 3.183063. So there we go. That was the Newton-Raphson method at work, enabling us to solve this otherwise impossible equation. Hopefully you guys enjoyed it. And yeah, hopefully you guys understand this derivation. So thanks for watching, and I'll see you guys in a future tutorial. Bye.